force downstream. This gives us an incredibly, reword that. This gives us the advantage of, we can now start talking about, there's an electric field in a particular direction, and I put an object into it, which way is it going to be forced? I don't have to talk about the source anymore. Now, there's still going to be some mixing back and forth, but eventually we're going to get to the point where we're really not caring what the source is. All we care about is what's the electric field at some particular point.
Could I ask a quick question?
Yep.
You had said, what's the electric field at a particular point? I assume you mean the direction, right? If you were to say what is
direction,
the
well, direction of the electric field to know which way it's going to be forced, yes. If I want to know what the force is, then I need to know what the magnitude of the electric field is.
Okay.
For example, well, we'll stick with the proton there. I have, I guess I don't have to stick with the proton anymore. I have an electric field going to the right at this point right here. The magnitude of my electric field is five times 10 to the 6th. What are the units of the electric field? Based on the stuff written on the board, what are the units?
Joules?
How'd you get that?
I don't know. I was
Sounds
taking
good.
a stab at it.
Okay. That would be just charge itself.
Well, when we had the electric force, it was in newtons, but we removed one of the Q's. So it would be whatever the full unit. I don't.
Remember, this is the electric field right here. So,
Yeah. So it's newtons over whatever the units of Q is that I don't remember. Coulombs?
yes, newtons per coulomb. And the powers that be said, you know, we're going to leave it like that. I can handle newtons per coulomb. I don't need to honor anyone else. So then I stick a proton. No, it's not more than just a proton. We're going to stick a charge here, some Q, where Q is equal to 3 microcoulombs. I'll just make I hat to the right. Although since it's a one-dimensional problem, I can get away with just a plus or minus, but I decided to make it a little bit special. I have. What is the force on the charge Q? Again, we don't know what's causing this. We can't go back to straight up Coulomb's law in order to figure out what the force on it is. But we do have other formulas for force now. I don't know the mass or the acceleration of this object, so F equals ma, probably not the best way to go about it.
Could you approach it the way you would in a, say, a collision problem where we took, I mean, it's not the mass, but like.
You're making it more
multiplying.
complicated than you need to.
Oh, okay.
You just multiply them together?
Yeah, pretty much. I go back to this again. The electric field is the force divided by the charge. Therefore, the force onto from whatever the source is just going to be charge 2 times my electric field created by the source. Now, I've given problems where I've had students find the electric field And they solve it, and then I ask what's the force on the object, and then they go back to Coulomb's law, or they get stumped because they can't figure it out because the situation's more complex than that. Yeah, this, an often overlooked formula. So, in essence, you're multiplying the electric field times the charge. The direction will be the same direction as the electric field, which is to the right. And so we end up with the force on Q is 15, what?
Newtons.
Daniel, you were about to say?
I was just about to say newtons because the columns should cancel out, right?
Yeah, or
It's a force.
you could, yeah, it's the other way of looking at it. All right, the electric fields. Questions before I erase? Right.
What you just wrote, the like 15 the force is equal to 15 newtons, is that entirely, charge, or is it, cause it's equal to the charge times the electric field,
Right.
so, I'm just a little confused, like, is there, like coulombs in that force, the 15N?
No, this is a Newton per Coulomb, and that's a Coulomb, so the Coulombs would cancel.
Right.
I feel like I missed the question. I did forget, there's one thing that was forgotten here, and someone should have told me on it. I had. So, is the issue you're having the fact that it looks like I should have like times 10 to something here, or?
I just thought it would be not divided by something, I'm just not sure, like, what of the 15 is charge and then what's the electric field. But it cancels out, so.
Putting some formality to it. So my charge is 3 times 10 to the negative 6 coulombs, that's Q, times my electric field, which is 5 times 10 to the 6th newtons per coulomb I hat. So it's just charge times the electric field that it's bathed in. So those cancel out. The coulomb cancels out with that coulomb, and I'm left with 3 times 5 or 15 newtons I hat.
Okay, that makes sense.
Okay. While I'm thinking about it. The last one. Any other questions? Now, recognize that we can now explain why proton or like charges repel or opposites attract. 2 different ways now. With forces, it's just naturally opposite attract, like repels. The hand gestures are backwards, but what I said was right. With electric field is if I have some charge, if it's positive charge, the electric field goes away from it. If I put a negative charge in here, it goes upstream. If I put a positive charge in here, it goes downstream. It follows the direction of the electric field. It goes opposite the direction of the electric field. If Q is negative, then just reverse it. But we have 2 different ways of explaining the exact same phenomenon, just different language. And you're thinking, hey, 2 ways is great, but can we have more? Yes, we can. We will eventually have 4 different ways of explaining the exact same phenomenon. But we're not there yet. Now, in terms of representing electric fields, they are vectors. They do add. The problem we did earlier, I don't remember what the answers are, so I'm going to ask you in just a second or in a moment. So that was 4 centimeters, 5 centimeters, 6 centimeters. That was 1 microcoulomb, 2 microcoulombs, -3 microcoulombs. The force on that one was negative, at this point, I need some refresher here. It was 27.2?
0.6.
0.6.
Negative 1.52 newtons I had.
1.5.
2.
All right, is that what we had before? And that's one of the things you missed. So that's question, so that's part A. Give you the configuration, say what's the force on it. Part B, what's the electric field where the negative, what is the electric field where the -3 microcoulomb charge is? We'll call it point P. The electric field at point P is, what is the simplest way of solving the problem, and what is the more complex way? Matter of fact, just tell me how we would solve it, and we'll identify whether it's the easy way or the hard way.
So you would take the force at that point and divide it by -3 microcoulombs?
Yes, that's the easy way. So we take the force on the charge that's already there, so force on 3, and divide by the charge of 3. And so we take -1.52 newtons I hat minus 27.6 newtons J hat divided by -3 times 10 to the -6 coulombs. And we end up with, well, I know it's going to be positive, I got that far. That's roughly 0.5. So that is actually slightly more than 0.5, so roughly 5.0, let's go, 03 times 10 to the 5th newtons per coulomb I hat, plus
9.2.
times 10 to the 6th, I would assume. Is it 5, what was this number really?
0.506.
6.
Repeating 6.
Alright. The simplest way of doing it, or I could have reversed it, I could have started, question A could have been what's the electric field at that point, and then I put a charge there, what's the force on the charge? This is the type of problem that the students who missed the fact that the electric field is force divided by charge, or the force is charge times electric field. If you miss that, you're just doing a lot of extra work that you don't need to do. So we're about to play around with some of this stuff, talk about electric dipoles, and any questions before I erase what we have here and stop talking about electric dipoles? Because I'm willing to bet when you woke up this morning, you were thinking, I hope we talk about electric dipoles today.
Is that about like polarity and whatnot?
I mean, it is related to polarity. It depends on not the polarity of an electric socket, more of the polarized molecule. Think about it, a water molecule where you've got a negative side and the positive side of the water molecule. Okay. Which does bring up some of the stuff that we're doing, just like before when we have box sliding down ramp and we said, let's ignore friction. And then we ignored air resistance throughout pretty much the entire course. We present some ideal situations, and part of the question that I would have had in my head is, how realistic is this? And so when you talk about dipoles, in essence what we're dealing with is, I've got two charges, some Q and a negative Q. I have two charges here that are a set distance apart. So say some distance S. Is that realistic to have two charges which are oppositely charged and then stay pretty much the same distance apart? And yes, it is realistic if we're talking about something like a water molecule. Because water molecules, you got oxygen here, you got hydrogen here. They're sharing an electron, exposing the proton core of a hydrogen atom, so we have a positive side, and then we have a negative side over here. The electrons that are creating this negative side over here are not being drawn towards the hydrogen atoms to the point where suddenly they disappear. So having an electric dipole is realistic at that level at least. So what I want us to look at is, if I am some distance away, so from smack dab in the middle, we'll call this big R, point P. What is the electric field at point P? So based on what we've done so far, what will be the direction of the electric field at point P?
To the left, towards the negative.
Why is that the direction?
My only guess is because the negative Q is closer to point P, and then the electric field should point towards the negative.
Yes. We do have two competing electric fields. We do have it pointing towards the negative and pointing away from the positive, but with that being closer, it will be the dominant one. Significantly dominant? Let's find out. So for the sake of notation, why don't we just go with to the right being positive. If you really like unit vectors, you can throw a unit vector in there. So the electric field at point P will be the electric field at point P from the positive charge plus the electric field at point P from the negative charge. I have two charges contributing to it. The electric field formula is this constant times the charge divided by the distance squared. What is the distance from P to the positive charge?
R plus half of S.
Say it again.
R plus half of S.
I want to give myself a little bit more room. Put the parentheses in. R plus S over 2 squared. And what's the direction of that electric field at point P?
Positive?
Yep. Plus negative, just go ahead and throw that one in, KEQ. So what's the distance from the negative charge to point P?
R minus, S divided by 2.
Squared. Now we're faced with this binomial in the denominator. It can become a real mess, but we're going to make some assumptions. First off, before we make assumptions, I'm just going to factor R out. So I get KE cubed, and when r comes out, the r is squared, so that's r squared, and I'm left with 1 plus s over 2r squared minus ke cubed, factor out the r, and I've got 1 minus s over 2r squared. Now it's so much more obvious, right?
You say so?
Is that all it takes? Wow. All of you are gonna get every problem correct on the first test. So it is spoken, so it shall be done. I don't even need to grade it now. All right, binomial expansion. Algebra 1. A plus B cubed.
A plus B plus A plus B, like A plus B times A plus B times A plus B.
Okay, I'll agree with that. Do you happen to know what it equals? All right, how about, we'll start out with A plus B to the first power. Let's start out with this. You know what? Because of where we're going. A plus B to the 0th power.
1.
All right, that was much closer to unison than I've been hearing. A plus B to the first. A plus B to the second.
A squared plus B squared plus A times B. Nope, I'm thinking something else. Disregard.
Plus 2ab plus b squared.
1a squared plus 2ab plus 1b squared.
That's what it was.
You left an ab off.
Okay.
A plus b cubed.
A cubed plus 2.
Not 2. There's a pattern here though.
I'm not gonna write this out. Is it 3AB?
Sorry?
Is it 3AB? I don't know.
Closer. It's 3a squared b.
Oh.